Pessoal, boa noite a todos. Bem-vindos a mais uma edição do nosso webinar do Comitê de Dados, Sistemas Inteligentes, da SP Brasil. Você já me conhece? Eu sou o Nicolas, eu faço parte junto à diretoria dos comitês técnicos, na parte de comunicação e mídias. E alguns avisos importantes, esse webinar será todo em inglês, então I will change to English now. So welcome everyone, and to our third edition of the webinar of the Data Intelligence Systems Technical Committee. And I will talk a little bit more about the Technical Committee's Office of SP Brazil. So we are a group with focus to promote technical discussions, to promote events in the main areas of industry. We have committees of reservoir, flow assurance, subsea, operations and maintenance, data intelligence systems, and decommissioning, and many others. So we promote events like webinars, like this online. We promote events like mini course only for SP members, and we promote technical forums in the main companies and events to like bio and gas, like oil and gas, maybe who knows. So if you're watching this and not a SP member, please become a SP member. It's easy. I will send you the link during this webinar, and also in the YouTube channel, I will send the link, the form, the Google formula, to you can participate with us in the technical data and many other comments if you are interested in. So for this webinar, I have here Robinson and Henrique, the chair and co-chair. For now on, is the director and co-director of the Data Intelligence System Committee. And I will ask you, if you're watching this, everyone who watching this, the questions will be answered in the final of the presentation. So I will call to our virtual stage Robinson and Henrique. Good night.
All right. Good evening, everyone, and welcome to another webinar of the Technical Committee in Data Intelligence Systems of SP Brazil section. Over the past months, we had hosted two very special sessions. In July was our inaugural webinar on Gaussian splatting and neural rendering with Professor Leandro Fernandes, exploring really cutting-edge methods for scene reconstruction and image synthesis. Later on in August, we welcomed Professor Marabel for the session on ontology, intelligence, and digitalization, where we discuss how well-founded conceptual models support data integration in the industry. Very interesting talk. Both recordings are available on our YouTube channel. Check it out. And we encourage you to watch them as part of this ongoing learning journey. That's our end goal here, right? Today, we're really pleased to announce we're going to continue our series with our third webinar. It's entitled Computer Vision in Asset Management. We are really honored to have with us Dr. Nasir Ashan. He's CEO of Abyss Solution. He will share his expertise in developing and applying computer vision and robotic technologies for large-scale infrastructure inspection and asset management. So get ready for a really inspiring session filled with valuable insights into the challenges and innovation shaping the future of our industry. Please, Dr. Nasir, you can carry on.
Thank you, Robinson. So, is this when I can start presenting?
Yes.
Yes.
Thank you very much. Thank you very much. Okay. So it's a pleasure to be here, and I'd really like to take this moment to thank Robinson and Nicholas and Henrik to give me the honor of presenting today. And I look forward to sharing our story with you. So my name is Dr. Nasir Hassan. I'm the CEO and one of the co-founders of Abyss Solutions. Some of you may have come across this company, and for some of you, this may be the first time. And so with that in mind, I'm going to give you a bit of background. And predominantly, I'm going to focus on one particular aspect of our journey. And that's going to be how we started to develop and enhance our corrosion classification. So today's talk is more about our journey. And the intent of today's talk is to share our learnings with the technical community, our findings, in particular, how this helps the industry. And hopefully the hits that we took will be good learning lessons for the rest of the people in the industry, and they won't have to make the same mistakes that we did. So thank you everybody for having me here. So I'm going to start now. So just a bit of fundamentals before I get into the details. We are essentially an autonomous systems company, and we aspire to build the future technology by pioneering. Our vision is to pioneer autonomy for inspections and maintenance at scale in the asset integrity space. And the mission is to develop that technology to make it accessible for everyone. It's very important for any disruptive technology to be accessible. You can build some very complicated technologies that can have an impact, but as long as they're not accessible, the world cannot use them. Not everybody can afford them, and it is difficult to make an impact in that way. So really our purpose is, our mission is to make it accessible. I do see autonomy as our global industries transitioning towards autonomy in the very near future. As sensors are becoming more compact, as power is becoming more packed, we expect drones and similar platforms to have longer deployment times 10 years from now. We expect, with the advents in quantum computing, Google and IBM have released some recent news you may have seen about the advents in the release of their first quantum computers coming soon. Let's hope that that's sooner than later. There's a lot of advents that are happening in compacting the mobile platforms and edge processing. As you can already see, NVIDIA has become one of the most valuable companies in the world. So there's a transition right around the corner that's happening very soon. And part of that transition is going to be autonomy. Autonomy is essentially the space that Abyss plays in. And I'll tell you more about that. So basically, the industries that we've delved in and move into have worked over the past 10 years. We were established in 2014, and we basically focused on the asset integrity space, and we played in a number of different industries. We started off in the water sector. We worked on a lot of water assets because we were based out of Sydney, and oil and gas is not really a prevalent industry in this area. We started off in Sydney because that's kind of where the technology was mostly developed, and most of the people that founded this company and were founding employees were coming from universities that actually developed this technology, including myself, being a researcher in the area. So we started off in the water sector. We worked on canals, imaging canals, analyzing the state of those canals. We moved into dams, water tunnels. We worked with a number of different type of platforms, including ROVs, AUVs, drones, surface vessels. Eventually, we moved into the port space. Also did some work in the port marine space with ports and shipping. We worked on civil infrastructure, including road tunnels and so on and so forth. And eventually in 2018, we made a step into the oil and gas space with some of our first work coming from Houston. And I'll talk a bit about that. Predominantly, we've been doing R&D before we really started to expand on one of our applications in the oil and gas space. And mostly we would go to clients and just, present ourselves as experts in the area, and we would get problems nobody else would really dare to solve. So our modus operandi was build the plane while flying. So a lot of our ideas, a lot of our innovation has come from a lot of the R&D projects. And what I will be talking about today was also started off as an R&D project and then eventually evolved into a product. So we've worked in multiple areas. I'm just going to talk about some of the solutions that we've provided in the asset integrity space. One of the biggest and focal streams of revenue for the company is external corrosion monitoring. And we have a platform called Abyss Fabric that allows you to visualize external corrosion. It allows you to be able to track it, look at it, plan your maintenance based on it, and it's one of the major streams of revenue for right now. We've also deployed similar types of applications and a lot of this is predominantly on offshore platforms, some onshore assets as well, refineries and onshore gas plants and so on and so forth. We've also applied similar technology to the marine terminal space, where we've not just looked at the top sides of these assets using terrestrial laser scanners, but we've also deployed our own surface vessel. So we've developed an autonomous surface vessel that can actually go under the docks of marine terminals, collect data. With marine terminals, we were also able to fuse data coming in from different sensing modalities. So we're able to use the surface vessel, underwater ROVs, terrestrial laser scanners, along with aerial drones. And we were able to combine and fuse the data coming in from these different sensors into a unified reference frame, where we were able to combine the information and the perception from each of these sensors and display it in a single go. One of the first areas that led us into the oil and gas space was a very high fidelity imaging system, which we call Lantern Eye. We developed that predominantly firstly for the water sector, where the challenge over there was to look through dirty, turbid water. Visibility was usually very low. So we developed this high fidelity imaging system to be able to, get the most advanced, most clear images in turbid water. Obviously, it also has limitations because there's only so much you can visualize. But when we entered the oil and gas space, they saw that as an opportunity. They said, fine, we don't have such turbid water, but it looks like a pretty advanced system. So the use case that came out of the Lantern Eye in the oil and gas space was high fidelity imaging for precision metrology. And one of the first applications was mooring chain integrity assessment. So we were able to co-develop this with Chevron, Exxon, and BP. And then later on, it was approved by ABS as the most advanced high-fidelity imaging system globally that was able to give you sub-millimeter accurate precision metrology with a 95% confidence interval. What was most interesting about this technology was it was invariant to the motion of the target, and it was invariant to the motion of the source or the platform upon which it was deployed, which made collecting inspection data for these things quite simple, because motion brings in a lot of complications, and you need sophisticated platforms to deploy and expensive platforms to deploy, lengthy inspections subsea. Finally, one of the other areas in the oil and gas space that we delved into was deploying perception systems on robots that would go around on onshore assets. This was a project we did with Shell a while back, where we were conducting operator rounds. So they basically had robots that were running around these facilities, and they were essentially interested in monitoring methane emissions. And they decided, this is a great technology to add on, and also look at, conduct operator rounds. So they engaged us with that on that project, where we developed a system that would learn what is normal and then eventually be able to predict anything that is not normal, and raise alarm bells. I'm not going to be talking about this technology too much today. I'm going to be focusing more on the external corrosion management. But these were the key areas that we explored in oil and gas, and I hope that gives you some context. So before I get into the details, Abyss Solutions is a accumulation of quite a bit of experts. Most of our people that work in developing the technology are PhDs in autonomous systems. And most of us also originate from the Australian Centre for Field Robotics, which is one of the largest field robotics facilities globally, and is quite well renowned. The founder of this facility was Professor Hugh Durant-White, who is a very well-known name in field robotics, particularly SLAM, one of the inventors of SLAM. And I had the privilege of being able to learn from him as well. Okay, so basically, the areas that we accumulate in terms of expertise includes autonomy, field robotics, computer vision, multimodal sensing, data analytics, and data science. The areas that we've been applying this technology to are spread across a variety of different industries, but the tech stack is pretty much the same. It's all about perception, planning, and control. These are the three pillars of autonomy that make a system more intelligent. Autonomy basically can be defined as the intelligence that a robot has to be able to understand its environment, improve its mission planning, and effectively execute through control, effectively the missions. So we've been working on this. We've worked in mining. We've worked on autonomous drills. We worked on, classifying geology. We've worked in deploying this stuff to map marine benthic habitats using AUVs. We've also applied this technology to monitor agricultural harvests, including fruits and vegetables, to be able to not only assess how healthy they are, but also how, how much the yield is. So, and not to forget space. We've deployed these systems for autonomous control and perception in the space field, mostly on simulated environments on our planet. So we started in 2014, and we're about 200 employees across the globe now. We bootstrapped this company with just 4 founders with very little capital. And it's a testament to the expertise of the people in the company that we were able to pretty much grow and attract a good amount of industrial projects to help the company get on its feet. Our 3 main centers include Sydney, Islamabad, and Houston. That's where our operations teams are, and our R&D teams, and our headquarters. But we've got regional offices in Rio, Aberdeen, Abu Dhabi, soon one opening in Saudi. So we essentially are working with some of the biggest clients in the industry. These include Exxon, Shell, Chevron, Total, BP, Oxy, and so on and so forth. Recently, we were also able to add ADNOC in the UAE as one of our key clients. And more recently, we also were able to get our technology approved with Saudi Aramco. So we're looking towards hopefully expanding in that region as well. But local to Brazil, one of our first NOCs was Petrobras. So I just kind of want to talk a bit about the tech stack. So autonomous systems are basically the role of autonomy in this industry that we are focusing on is to complement inspections and remediation. And the way we look at it is to collect data, analyze it, and then to be able to act upon the findings that we have collected. So acquisition involves a number of different sensing modalities and a number of different sensing platforms that can be deployed to enable those sensing modalities. These include a variety of different sensors, from terrestrial laser scanners to aerial drones with optical cameras, to underwater ROVs with sonars and optical cameras, and with surface vessels. So these are the different platforms that we use to acquire. Predominantly, the data that we work with includes visual. A lot of the information that we get is out of visual data, but we complement it with 3D geometry by using laser scanners, sonars, and so on and so forth. The analyze part is taking that data and trying to be able to pick out faults. Traditionally, we used to look at cracks, fractures, fabric rupture, depending on the asset we're looking at, whether it's a water canal or a dam wall, or a pipe or a sewage tunnel. And eventually we moved, when we entered oil and gas, we started getting into corrosion. So external corrosion is a pretty big problem across the industry, and I'll talk about it shortly. The ability to pick up these faults is in the order of 4. So we are basically, we first detect the problem in the data. Each image is geo-registered, so we're able to attach a geotag to any of our findings. Once a defect can be geo-stamped, we're able to then locate it spatially. So once we detect it, we classify, we quantify the problem. And this quantification allows us to get into the act side of things, because now we're able to start planning. So we're able to prioritize the faults and give to the client information that will allow them to plan the remediation. Obviously, problems are always much more bigger than budgets. Therefore, it's very important to be able to prioritize your faults. And this is not limited to just looking at the fault itself, but also the ability to take into context the importance of what the fault is on. And so that's where we come into planning. So let me talk a bit about the problem. External corrosion is one of the 3 biggest OPEXs. Fabric maintenance is one of the 3 biggest OPEXs for any offshore operators that we have come across. It is a major problem. Corrosion itself is a $3 trillion problem in the industries globally. It's a huge market. When we first entered this area, the clients were telling us, and every client we ever talked to basically told us most of them are in catch-up mode. Catch-up mode is basically running around trying to get ahead of the problems, but always being behind. It was a very vague definition. It was confusing. We didn't quite appreciate the depth of it back then, but over the years, we've learned quite a bit about the problem and managed to give you a better articulation, which I will do right now. Let's use this example that I've got over here. Just taking data from 4 platforms, one of them, for example, that we rescanned. The backlog, which typically is defined by operators as the number of work packs in the system that need to be addressed, that's a traditional definition of backlog. But really, backlog is the items that you do need to address that haven't been addressed. We typically looked at, in this example, we looked at medium and heavy corrosion, which I will get into in more detail about, but just let me give you a high-level definition. These are usually severe versions of corrosion, significant flaking, You can see geometric deformations, probably bumps, blisters, so on and so forth. And we typically chose this for, we looked at these problems on process equipment. Process equipment is critical equipment, which is doing the production. Now, if you look at these platforms, you're looking at, if you look at the second column, year 2, looking at some pretty big backlogs. The repair rates typically average in the industry from 6,000 to 10,000 per year is the average repair rate that an operator typically deploys to go out there and fix things. And repair does not mean painting. And repair is an expensive process as opposed to painting. The goal is to remove as much we can from repair and detect things early so that we could just address it in painting. As you can see, the backlog is much larger than the average repair rate for painting. We were also able to go into these platforms, particularly the ones that we rescanned. And there's more than just the one that I listed here. And we were actually able to analyze and track over time, because we've got temporal scans, what has been fixed and what hasn't been fixed. What's new, and what has creeped. So as you can see, if your repair rate is lower than your backlog size that you need to fix, problems will creep. If you look at the first platform, the backlog actually doubled in the course of the 2 years. And the reason why this happened when we looked at it was 63% of the most severe problems in year 2 were actually less severe in year 0. And so this indicated that if we don't address these problems, they actually creep. So we came up with this new term called backlog creep. And backlog creep is a big problem, because if your repair rate is more or less 2 to 4x smaller than your backlog size, you're always going to have a backlog creep, which means you're always going to have your backlog growing. If you put that down on a graph and you simulate it and you assume your repair rates remain the same, your backlog is going to significantly increase over time. And you can draw an imaginary line somewhere and say, okay, if we don't take care of this problem before then, somewhere in the course of that upward curve, something bad is going to happen. And either we're going to get rid of the platform and sell it off to somebody else, or it's going to sink to the ground. So this indicates that some mode of intervention does need to happen to be able to get you to a state where your backlog size should be more or less equal to your repair rate. Some form of intervention is required. And this is kind of the future of where we intend to go, is to be able to to use robots to be able to address these problems, so that you don't have to send more humans there. And this is something that is now, because of our temporal data, starting to become a concept that the industry is becoming aware of. And and so we came up with basic definition of maintenance mode, which is your backlog is equal to your repair rate. Really, that's when you can sustainably defend and maintain your program for maintenance. So this fabric, and I'm using a very old image of our system over here. As we started, in fact, Paulo, one of our regional managers, the one for Latin America, for South America, was quite insistent that we use a very old image over here. This is basically showing you one of our very first instantiations of Abyss fabric, where we were displaying corrosion on a platform and classifying it into different categories and being able to measure it. So this is the platform that I'm going to be talking about and our journey with it. Before I get into the details, when we got into the area, most of our clients basically had collected terrestrial laser scanners based data. So it's basically a laser scanner. You take it there, you place it somewhere on the platform, and it collects a 360 image of laser data and visual data, and it gives you sphericals. Back then, terrestrial laser scanners were still a pretty new concept. This was early 2020, okay, 2019 to 2020. Not many people were collecting, TLS data or laser data, but this was one of the first set of data that operators started presenting to us and said, "Can you detect corrosion on this?" Now, 3D data is very important, because just detecting corrosion isn't enough. You need to know the context. You need to know where is the data? What is it on? Classifying corrosion just based on visual imagery is also insufficient. You need to be able to have some 3D aspect, taken into context so that you could be able to look at more detailed classes of corrosion. Corrosion is not just about, downloading a content off the internet and, just running it. There's a lot of minute aspects to it, as I will explain in the journey that we've learned. But the 3D data gives you context, it gives you spatial awareness, it gives you precision. And the reason why it's important is because you can use visual imagery to detect corrosion and overlay it on different things. But at the end of the day, if you're unable to completely address the problems posed by the industry, and you're unable to identify everything, the goal here for the operators is to replace personnel that are doing visual inspections with systems like these. Visual imagery can only get you so far. You do need to take into account 3D data so that you could address the entire backlog. If you're unable to do that, your system will not be able to replace, people. It's not going to happen. The completeness is a critical thing. Completeness of coverage, completeness of being able to understand how much you've covered, what you're missing. These are very important concepts. Otherwise, the adoption of the technology, as we have learned the hard way, is not possible. Every operator will ask you, great, I'll use your system, but I still have to send people over. This is a repeated concern that has been raised to us by almost every operator we've ever dealt with in the field. So if your system cannot replace the people, there's no point. So we have come to realize that you do have to have 3D data in order to address the problem completely. So it also impacts things like isometrics, PNID redlining, CAD model updating, and the quality of the analytics in summary. So we basically, when we started off, we had a very basic system where we were just detecting corrosion on these sphericals. And we realized certain problems with that system. Particularly, we were trying to predict severity in the first gen of our models. Severity is a concept that changes from one operator to the next. Everybody has their own standards of how they want to run their maintenance program and how they're designed to send people offshore to address these problems. Severity is not what they're interested in. We, weren't successful in it with our first gen model because we needed really systems that would be able to customize and, adapt into their integrity programs. That realization led us to the second gen, and I will talk about this in more detail shortly. In our second gen, we were able to more easily adapt into customer requirements and map into their business logic with our models. Those models also enabled further data to come in, but really the data volume that varied from first gen to second gen was also a function of the fact that we were still getting more data coming in from clients. There wasn't a lot of data coming in initially, but then more data started coming in next. Really, the third gen is where things changed, where not only our definitions evolved into, for corrosion, evolved into the business logic quite easily, but we were able to train our systems to work on 10 million images. So I think that was quite a big milestone. Our corrosion detection system now actually is trained over 10 million labeled images. I've not come across any other system globally that is as sophisticated, across these many images. So it is, to the best of my knowledge, the most advanced system for modeling corrosion globally. And what's more important is that it is able to generalize and take into account data across the globe at different times, across 34 deployments. So it is certainly a major milestone that our company has reached in terms of developing the most sophisticated perception capability for coding breakdown. corrosion. The accuracies of our model, including the F1, precision, and recall, have significantly evolved over time. And this is a function of how we classify the problem. How do we set up the corrosion problem? What are the key components that go into it? And the data collection aspect of it plays a big part, including quality control. These are three key pillars that I'll be talking about shortly. The architecture evolved from just basically being a simple ConvNet for semantic segmentation to having a probabilistic layer so we could start using uncertainties to eventually moving on to a transformer architecture where we were able to take a lot of context into account and be able to model the variability and the data set shifts that come as the models expand across a variety of different platforms across the globe. So Gen 1, I think, let's focus on that a bit. In Generation 1, we basically were looking at three different classes of corrosion. We were looking at predicting light and moderate and heavy. As I mentioned earlier, light, moderate, and heavy indicate severity rather than corrosion defects. And that level of severity differs from one operator to the next. Different people classify severity in different ways. Initially, we had a few data sets. We're predominantly just looking at training the models over a single platform and just predicting over the rest of it. Not really looking at taking that data and scaling it to other models or other platforms, sorry. And we did manage to achieve through some initial competitive pilots with some of the majors, pretty good accuracies. Particularly, we did attain through some of these competitive pilots, heavy, moderate, and light were 97% accurate, 92% accurate, 91% accurate, and we outperformed our competitors and started delivering projects. This led to the client saying, okay, this works, you guys are good, you know what you're doing, so let's start giving you more data. As we started getting more data, our models actually started to fail. And we started realizing this, and we alerted our clients as well, and they were like, okay, this is a problem. So as you start scaling and your analytics start failing, you start to realize the complexity of the problem. The main thing was generalization. Generalization was a huge issue. Different times of the day, people are collecting the data. The invariances weren't modeled properly. We were predominantly initially just looking at predicting corrosion, external corrosion, or classifying it on process critical equipment, but then there's the floor, the gratings, the handrails, the structures. All that context was starting to confuse the problem. So what we realized was also the mapping isn't really translating into what the client wants. Light, moderate, heavy doesn't make any sense for some. It makes sense for maybe a couple, but it doesn't really make sense for some. And our accuracy metrics started to drop significantly. So one of the interesting things also that we realized early on with light, moderate, heavy was that the subjectivity was a pretty big issue. We did a pilot with one of the major operators, and what we realized was the subjectivity. We basically did a pilot where we took some inspection experts or engineers, and we gave them the data. We asked them to label it, and what we found out of that study was up to 60% disagreement. This is very, very significant. Now, if one engineer thinks it's a problem and the other engineer thinks it's not a problem, where do you spend your dollar, right? This is an industry-wide challenge, and it is still a challenge. In fact, in 2020, IBM presented in the Machine Learning Oil and Gas Conference in Houston in 2020, I think. They presented some results where they did large-scale visual sequential analysis, and they reported within 15 minutes into the analysis, which is done manually, the error rates go up to 50%. 50%. The variance in the agreement upon labeling for ground truth is a huge problem. So being able to collect good training data to be able to consistently and objectively predict corrosion, this is a huge challenge. It's not an easy problem. So how do you restructure the problem so that you could be able to do that is something I'm just going to talk about shortly as well. So as you can see over here, we've got some examples. Red is heavy, yellow is moderate corrosion, light is, light is I think blue or cyan, I can't remember. But if you look at this particular patch up here, okay, when I look at it now in retrospect, it actually doesn't look like, it looks like heavy corrosion, but it's labeled differently. I'll also show you some more examples of subjectivity later on. So in generation 2, we decided to turn the problem around. Instead of trying to classify corrosion by severity, we decided to just start detecting features that compose different classes of corrosion, and let the client then map their business logic into what we've detected. So we decided to break it down into 3 different classes. Well, you look at the diagram on the left. So coating breakdowns, basically corrosion in general. Within that, you've got 2 different major classes. You've got corrosion and you've got paint peel. Corrosion itself has corrosion nodules and scab scaling. And paint peel is basically just paint peeling off, right? So we decided to start focusing on coating breakdown as being everything else apart from, within coating breakdown, everything else apart from scab scaling and corrosion nodules. So be able to detect coating breakdown and then be able to classify scab scales and corrosion nodules. So you can see some examples of scab scale over here. Some pretty ugly looking corrosion. And you can start, and on the right, you could see examples of corrosion nodules. Now, these are pretty severe versions of corrosion because this means, oxygen and water have peered through the surface and interacted with iron and start to push upwards. You start to get these bumps and blisters on the pipes. This is quite serious, particularly on process critical equipment, because it starts to indicate that there may be some wall loss happening over here. Scab scales are also quite conducive, quite severe if they're happening on process critical equipment, so they definitely need to be detected. And then coating breakdown is everything else that we can see that's happening. So we separated the ML outputs from the business logic, and you can see at the bottom right, we're detecting different features that compose corrosion. And then we take a mapper that kind of maps it into severity. This makes it much more scalable for different clients as we get into the industry and start to interact with more people, because then they can apply their business logic or their mapper into different levels of severity. We also were able to then develop different scales for coating breakdown as well by looking at RI scales. So get a sliding window going through. So anything that's coating breakdown, but not scab scale or corrosion nodules, you can start to rank that by looking at the dispersion of corrosion or the density of corrosion and how it's spread out across 5 different scales. This is typically a logic used by most operators. Some use RI0 to RI5, some use RI0 to RI7, 9. I've come across a variety of these scales, and they have their own definitions. So we just take their definitions, we detect corrosion, and we just run the sliding windows, and we're able to calculate based on their metrics or their scales the distribution of coating breakdown. So redesigned our labeling SOP with an acid integrity SME. So we couldn't have done this without the subject matter experts. So they basically helped us design this classification system. And then we trained a suite of models targeting specific corrosion elements. Most importantly, with this new classification system, we were able to use visual and geometric features combined from the point cloud data and the RGB data. Now, this got our model performance up to 72% when it comes to the F1 scores. But again, it wasn't sufficient to meet client standards. Client standards are quite high. Ideally, they want 100% coverage and they want 100% accuracy. Well, that's never going to happen with machine learning systems. And what's interesting is the journey was difficult because even convincing the clients that you're never going to get 100% coverage and 100% accuracy is not easy, because they think their inspectors are covering quite significantly. Well, to be fair, I mean, many people do realize that, but it is a major decision-making leap for them because they're moving from a manual inspector to a machine. So the machine needs to provide more proof that it's actually getting greater coverage as opposed to an operator, because it's just a big leap of faith when it comes to that. You just have to see more data. So we started coming up with ways on looking at blind spots. These are some of the issues that we started coming up with. Where are we not collecting the data? How do you place the data scanning samples so that you can get maximum coverage? How can you maximize coverage? And how do you report what's missing? It's very important to report what's missing, because this gives a big level of comfort to the operator. What we also started to realize with Gen 2 was that our quality control for the client started to get pretty heavy. It wasn't scalable. You can't just go out there, predict corrosion, and then come back and tell the client, this is what we predicted. You have to ensure that they get it up to a certain standard. But with Gen 2, that cost started to go up significantly, which made it extremely difficult to scale this technology across the different growing demand that we were getting. Because you just have to get people to go in and just make sure you didn't predict things way out of bounds. And I'll talk a bit about quality control shortly. So you can see some examples over here. One of the interesting things that I'd like to talk about here is also the corrosion nodule prediction. So when you detect coating breakdown, then we have a second layer of models going in to look at scab scale and corrosion nodules. Both of them are different. Corrosion nodules is less of classifying it. It's more about quantifying the height of the blister. It's very critical, particularly for mechanical integrity, because the height of the blister actually indicates potential wall loss. So many clients, each of them have their own rule of thumbs. They say if your height is this much, then we estimate the wall loss might be this much. So we need to be able to measure the height in an effective way so that we could plug in their business logic to estimate the wall loss. And every client has their own rule of thumb. So what we did was we trained a regression model that would then be able over data that would be able to then be run on the point cloud and be able to predict the height of the blister as it runs over it. So this was quite good. We were able to get about 92% accuracy with a 65% confidence interval over thousands and thousands of samples that were trained. So that started making our corrosion nodule critical thing quite good, because then you can start to minimize the false negatives that you will get over here. So let me go to the next one. So Gen 3. So because of these problems and because of the lack of generalization, we started to upgrade our architecture. And this is what Gen 3 is basically about. And the main step change over here is that we started to adopt transformer architectures. And this enabled us to take a lot more context into account. So traditionally ComNets focus in particular areas of the feature space. But what transformer architecture allowed us to do was to take advantage of the fundamental neural network architecture, which was to be able to take all of the context into consideration. However, traditional neural nets were not very effective or efficient, and ComNets really started to bring in the efficiency. Transformer architecture combined the best of both worlds. So you take areas to focus on in the feature space across all the data with the transformer architecture. What it also enabled us to do was to start taking context into account. We were able to separate the feature space into more separable classes of corrosion. Even if we're trying to predict coating breakdown on the platform, we were able to take into context coating breakdown of process equipment versus coating breakdown on different types of structures. So just learning that context in of itself makes the feature space more separable, resulting in higher precision, better recall, and it was quite important. The other thing that was quite useful was to be able to take into account context windows without going into too much detail. Context windows provide you, again, more perspective. All of these added new features started to bring in the ability to model variability within the data and make the supermodel more robust to that, so that the decision boundaries are more regularized and less variant. Even though the model is much more complicated, we're actually making the classification problem simpler, because we're creating we're basically reducing the overlap between classes. This transition from Gen 1 to Gen 3, the key thing over here is that noisy labels will happen because your classes are just not well defined, or your features are just not good enough. So the best way to overcome noisy labels is to be able to either redefine your classes, okay, like we did, and also to be able to take more features into account that will allow you to separate these classes. And the journey that I've outlined so far allowed us to do both these things together. This improved our performance to over 80% now with the F1 scores. Our precision and recall also similarly went over 80%. But here's the most interesting thing is, and I'm going to talk about verifying and validating as well shortly, but we were able to compare the performance of our models with actually human-based prioritizations. So rather than predicting what corrosion looks like, we're actually able to compare what the output would look like. So how would the operator prioritize their paint blocks? When we started correlating our model performance with that and mapped it on to paint block prioritization, we started getting 90 to 95% accuracies on how we would prioritize the paint blocks, particularly for coating breakdown. So these enhanced generalization across platforms, lighting conditions, and environments, was a byproduct of the change in the architecture, the way we model the classes, and the way we influence quality control, which I will talk about shortly. And you can see some examples over here. Now, the MLOps journey. So just detecting corrosion isn't enough. Scale is really where the problem gets difficult. So initially in our Gen 1, in our first version of the machine learning operations pipeline, we were basically manually touching up. So once the model predicts, we manually touch up the labels, then we have a full quality control review, and then we deliver the deliverable to the client. However, that's not how it should work, because it started creating a lot of burden on quality control. The problem became, trying to patch up what the model wasn't doing right, so we're not misleading the client. So we started investing a lot heavily on quality review. And that started actually posing a problem, because when people go in to fix what the model is doing, you're actually taking away the objectivity and bringing back in subjectivity. So how subjective is your assessment at the end that you're delivering to the clients? The clients were very sympathetic and considerate. They understood these problems. They were understanding, and they stood by us while we were fixing these things. So in our MLOps version 1 of the pipeline, we basically moved on to fine-tuning our models. So once the model predicts, if we feel the model isn't good enough, we go in, we patch up some of the labels, we feed it back into the training, back into the model, and then we output the model again. Now, what this was doing was it was taking in the subjective assessments, and because of our improved architecture, it was able to then objectively discern between the disagreements on the labels that we were patching up, and it output a more regularized version of the model, which would result in a more regularized or generalizable objective assessments. We started looking at model variances through consensus testing as well, which I will talk about shortly. And we were able to correlate the output of our machine learning deliverables, as I mentioned earlier, with actual deliverables that the operators would use. So, for example, if operators would go in and look at their traditional assessments and prioritize paint blocks, we would use our machine learning algorithms, go in there, predict coating breakdown, use that to prioritize paint blocks, and compare that to how humans would prioritize it. So at that macro level, the individual subjectivity of labeling is reduced, and you're getting this macro or minimized, and you're getting this more macro view of how you need to focus your painting program. So I think that helped a lot in terms of being able to translate the output to the clients as well. and to be able to deliver a more consistent product. So the consensus test set I'm going to talk about in the next slide, and how that worked. So you can see over here 3 different images annotated by 3 different humans. As you can see, if you can follow my mouse, basically around here, this person thinks less of corrosion as opposed to this person and this person. This person is also missing this spot, as you can see on the bottom left corner, as opposed to this person and this person. As you can see, the labeling is not the same. Now, why is this important? This is very important, and this is why 3D information is also very important, is because if you don't accurately estimate the surface areas, you're going to start affecting, you know, the accuracy of your RI scales, or eventually how the people would prioritize their paint blocks. So this accumulates. It's just like an inertial sensor. With more drift, the error just accumulates. With every image, the subjectivity just adds up and adds up and adds up, and affects your overall objectivity of how you prioritize things. So there are ways that we manage this by, if you look at it, so we combine the 3 together. You can see the blue areas are where they disagree. Okay, if you look at the disagreement, it's not insignificant. The model needs to take this into account, and the quality control process needs to take this into account. Otherwise, your product's just going to be a flaky product that's just going to result in one performance at one time, another time. So we looked at what we predicted, and then you can compare that to this. In the quality control process, we basically started to run these and or operations. So we were looking at, you know, how, you know, where do the labelers consistently agree and where they don't agree. And then you can use that to start influencing how you actually quantify the false positives and false negatives. For example, where they do agree, and where, you know, if there's a true positive in the and the or operation that you run across the whole test set, you can start to favor the true positives across both operations, but you can focus the false positives and false negatives more on the and side. And you know, that's kind of, you can start deciding the logic of this, but at least you get a framework to start looking at performance. My key takeaway that I want you guys to take out over here is that detecting corrosion is quite easy. It's really making a scalable product that's very difficult. How do you consistently, repeatedly, reliably, you know, deploy the same system so that you could scale across everybody's problems? So what's interesting over here is that as we started to, what I wanted to show you on the left side, or the box whisker plot over here, is that as we started to add more patches into our validation process, the variance around the F1 score. So let's not focus on this F1 score. This is an old F1 score from an old plot that we generated. But the variance around the F1 score significantly goes down, right? So so really the test set size is quite important, and you can determine it to actually get an objective method to understand, okay, now you've got statistically reliable you know, model, because the variance is quite low on the test set, and you can start to use this and trust its predictions and its uncertainty to start driving QC based on uncertainty estimates. So if I go to the next slide, you can see that if our F1 scores are quite reliable, which is 50% of the time, you know, we don't really need to do any fine tuning. If they're not reliable and the variance is good enough or low enough, then we basically go back and add a few more to bring the base model back up to speed. If that still doesn't work, then we need to send in people that focus on the uncertainty of the model. So we use the uncertainty to start driving QC. You see, if you don't have a reliable model, you can't rely on the uncertainty that it generates either. And in order to understand how to rely on the uncertainty, you need to understand the variability in the F1 score. So that variability can be thresholded, and then you can use that to say, okay, now I think the model's good enough. So if it's not sure about something, That's really where I need to send the humans. But if you don't have a reliable model, you can't trust its uncertainty. You can't control the QC process. So basically, what you're seeing on the right over here in this graph is when we start to correlate our F1 scores with the actual, client deliverables, the larger the block sizes, you can see the blue line on the top. The F1 scores are pretty high. So as I said, the subjectivity starts to dissipate or dissolve by the size of the block, within the size of the block. And you start to get higher F1 score. You start to get correlations with even at low F1 scores. But with smaller blocks, like 3-meter size blocks, you can see the real trend over there. So we kind of cross the 80% F1 score as we, and the correlation starts to cross the, with higher F1 scores. It starts to correlate much more significantly with smaller blocks. So basically, the correlation in all cases is pretty high, as long as you can trust your F1 score. So this is a good metric to start to realize, okay, now we can trust our F1 scores at this point, regardless of the block size. So let's start using its uncertainty to fix up and finalize it. More recently, we were able to actually not even have in the last few deployments any human involvement, because we've developed this framework to come up with an objective way to do this. So I think I already talked about this. Just one last thing I do want to mention over here is that as the number of so our base models start off at a pretty high score already, like 70%. I'm just giving you some examples. Focus on the black curve, okay, the solid black curve. As we increase the number of scans, we don't need too many more to cross the 80% F score, F1 score or performance. And therefore, not much fine-tuning is required. In some cases, like the red dotted line, this one over here, we didn't even need any fine-tuning. But in the two platforms that I'm showing you over here, just with the star platform, we're basically just able to add one more set of scans before we started getting into the comfortable zone. And our ops target is usually to hit 80% F1 score, which is this green line, and then the blue line at the top is our ML target. So now I'm just going to show you a bit of what it looks like, and I'll let the video speak by itself.
To the digital walkdown tutorial. This short tutorial highlights how Abyss Fabric streamlines the inspection process, enabling you to perform comprehensive digital walkdowns remotely. As you can see, a 3D view of the platform is already open on the viewer screen. You can navigate around the platform using your mouse and by holding the Control+Click button. On the left side of the screen, you'll notice the Query tab. Here, you can search for assets. Use the Equipment tag option to directly search for an asset or filter by service group and size to locate the desired asset. After applying the query, a list of assets will appear on the right-hand panel. From there, select the asset. In this case, we've chosen a 6-inch diameter drain line that spans the entire deck. Once the asset appears in the viewer, use the visibility settings on the left-hand tab to visualize the corrosion and coating conditions in the 3D point cloud. Now, use the Find Viewpoint feature to see relevant images. Click on the spherical thumbnails within the right panel to switch between spherical views. Once in the spherical view, you can inspect the asset closely, focusing on areas of heavy corrosion. The corrosion and coating filters will provide better visualization. Once you've identified a specific area of interest, click on the menu button to open the panel to add a point of interest. Zoom into the selected point and turn on the point cloud. Click on the Corrosion Under Pipe Support (POI) and select the exact location where you want to place the notification. Fill in the required fields and, if needed, add details such as scaffolding requirements or other observations. When you're finished, click Add POI and then close the image view to return to the 3D point cloud. Review the added POI to complete the process. This concludes the digital walkdown.
So I think the video kind of just showed how to visualize all the analytics that come out and how to make use of it. And that's basically what the platform is intended to do. So what are some of the benefits that come out of this? So predominantly one of the one of the main drivers. So there's two areas that we impact. There's mechanical integrity and coatings. These are two workflows within the operator's fabric maintenance program that we're able to influence. Mechanical integrity can plan their inspection campaigns and prioritize really where to go and do NDT. They basically need to make the decision of whether the part needs to be replaced or painted. And therefore, based on that, they can more effectively target areas that can be painted. They can identify areas for early painting, so on and so forth. So you basically, in that process, are starting to optimize your resources. You can spend more people on painting, or you can spend more people on repair. You can reduce your POB, reduce the burden from GBIs and reallocate them to getting more work done. All of that towards the goal of trying to hit maintenance mode. Remember that all these guys are in catch-up mode. They really need more effective techniques to reallocate and get more throughput. And essentially, this is the key thing that our technology enables. I think one of the other things that comes out of it is when you're doing all this, one of the things I didn't talk about too much was the contextualization of the asset. So just being able to detect corrosion isn't enough. You do need to be able to understand when it's on. Is it a pressurized gas pipe? Is it pressurized liquid? Is it a water line? Right? So that you could be able to prioritize. That contextualization is something that Abyss also has perfected. And it is still a semi-automated process, but last I remember, one of the contractors that was trying to contextualize the entire asset spent over 150 people for more than 14 months, and they couldn't get a 10,000 ton topside done. We're able to do this in 2 months with a very small team of people in operations. So that context is also very important. The contextualization needs to be quite accurate, because if you're not accurate with your contextualization, you could start to take into account low priority areas or low priority labels. So you could be, for example, labeling something as having corrosion, but it's included in a low priority, under a low priority label, because the contours for your contextualization just aren't accurate. They need to be dead accurate. Because if you mischaracterize the priority of a component or corrosion on a component and you assign it to some other priority level, you could end up with some pretty serious mistakes. So it's extremely important to get the digital twinning right. So that's something that also comes out of this. Redlining is another thing that comes out of this as a byproduct, because we are covering quite a bit of the asset, and the completeness is quite extensive of the data collection. We're able to also compare that to as-built with CADs. Now, the problem with CADs is you can take CADs, but the CADs are never really close to the as-builts. So that any people that do rely on CADs, they face the problem that they will never be, they're going to hit a brick wall pretty soon, because when it becomes time to replace the visual inspectors with that, CAD model-driven technology, the completeness can never be guaranteed. So you do need to be able to know what you're missing, right? And you do need to have a thorough data collection process to do that. So those blind spots where you're not able to, also the ability to analyze blind spots is also quite important, because then follow-up inspections can be organized over there. I think, there's, I don't need to go through all these benefits, but there's significant benefits that I talked about primarily. But then there's also things like, this can reduce the need for isometrics. You can start using this kind of stuff to just directly annotate on the system, so on and so forth. It increases throughput, reduces time. One of the key benefits, particularly for the coatings department, that we are able to achieve is increased liquidation rates. So with the same amount of people, they're able to more effectively apply paint on targeted areas and optimize their painting program. Paint people are usually very tight for budgets. So the ability to increase their throughput without increasing people is quite significant. And that is a byproduct of better prioritization and targeting. Now, I think I've spent quite a bit of time, so let me just talk about the last thing. What's next? Well, next is always bigger than what we've done so far. So there's a whole bunch of things that we do need to do. I think some small, some quick short-term adjustments include unifying the models within a single model, leverage the learnings, utilize active learning to transfer corrosion model capabilities to detect and characterize to new defects. I think new defects is something we're starting to look at. We're starting to get requests for dissimilar materials. We're starting to get requests for malforms, abnormalities on structures, which are not just corrosion related. There's a whole bunch of things. Daylighting, hot bolting, a whole bunch of these things are coming up. We've already been providing some of these services, but to be able to scale our models in this direction, I think requires some additional work. Generalizing the low-cost sensors. So we've been relying heavily on TLS or terrestrial laser scanners. These are expensive data sets. You can do them once. You still need to do them if you want to get the thoroughness. But to be able to then unify that with low-cost sensors to reduce the cost and reduce the burden of data collection going into the future, I think that's a key area. But one of the most important areas is the path to maintenance mode. So as we identify these problems, as we track them, as we can start tracking repair rates, actual repair rates, actual backlog sizes. We can start to build a very strong case, which we have now, and some operators are very interested in this and starting to work on this with us, is to be able to start arresting corrosion. So our goal is to get drones on these platforms so that they're arresting corrosion, so that we can hold it before the limited inspection teams and the coatings teams can, in a more sustainable way, get to them in time. The problem is, if they can't get to it in time and it's not held, the problems are just going to keep increasing. So it is extremely important. We can, give as many insights as we want, but until we don't own the value chain and can fix these problems, we won't be able to help the industry get into maintenance mode, take fabric maintenance from one of the most expensive OPEXs to being one of the least expensive OPEXs and the most cost efficient and effective and least risky operations for offshore oil production. So that is it from my end, and I will switch back to you guys.
Okay, Nasir.
Over to you.
Thank you very much for our presentation. That was very insightful, very rich presentation. And now I'll call Robson and Henrik back to the stage. So, Robson, you can talk a little bit, Henrik, about the sides of this presentation. For now on, we don't have any questions in the chat. Let me see.
Yeah, if there's no question in the chat, I have plenty. So.
Yeah. Okay.
Go ahead, Henrik.
Okay, so I have a question, and maybe to start with the last thing you talked about, right? Because that's fresh in memory. So you talked about arresting corrosion, and just remembering back to my university days, right? And corrosion technology, and the way they develop. Like, how sensitive is the technology today? Like you talked a little bit about categorization. One type of corrosion that I remember that typically is the starting point is a pinhole corrosion, right? You have just a single point of a break in the surface treatment. Are you able to today map those, and do you do that already? And I guess this would be an excellent starting point for arresting corrosion as well, right?
So subsurface is difficult, but if it's a pinhole corrosion that is visually apparent, then we can pick it up. But predominantly, we're targeting, corrosion nodules. So if there's a blister that's forming over the, under the paint, so even though the paint hasn't kind of broken up, the corrosion nodule is resulting in, or that leak or that hole is resulting in some kind of pressure building up from inside, pushing the paint outwards. It would embody itself in a blister. So we are able to detect those, yes. And like I mentioned, our ability to detect that is down to the sub-millimeter level. And this is also one of the reasons why TLS is quite critical. If you don't want to miss those kind of things, just doing that off visual imagery itself, it wouldn't be enough, because the accuracy of the photogrammetry, the accuracy of that just wouldn't be sufficient to be able to pick up things like those.
And do you let's say, when you do these type of surveys, do you typically present like I guess you do, but just to confirm, it's like statistical breakdown, how much is in each category, and kind of look at the movement between the different categories as well?
So the movement between different categories definitely requires a temporal scan. So you need to have at least 2 scans in time to be able to understand what's moved and what's not moved. So if a point has evolved in its fault evolution process, you do need 2 scans to do that. However, if we just do 1 scan, we're able to at least categorize and statistically represent, what is the breakdown between different faults. We're able to provide those dashboards. Each client has their own way of viewing it. So we kind of just leave it to the client when we get there and customize the dashboard for them, depending on how they want to prioritize and visualize their problems. But yes, the basic analytics are there to do that.
So I have one more question before I give the word to Robinson, right? So you mentioned temporal scanning, right? So the big question is, how long does it take to do these types of scanning, and how often do you set, let's say, aspirationally, would you like the scannings to be concluded, right? Because I assume that if you do it manually, it's quite labor intensive, and that might be a limiting factor, or will be a limiting factor. But we are now moving towards technologies that can do this more autonomously, like you indicated as well in your presentation, right? So what would be the ideal timeframe?
So it depends on the type of the survey. If you're going to be surveying a comprehensive and thorough data, you're going to be, your interest is to get a comprehensive and thorough understanding of all types of corrosion across your asset. You need a dense sampling strategy to be able to take the laser scanners to be able to do that. Typically for a 10,000 ton topside, we would take about 2 to 3 people for 3 weeks, 2 to 3 weeks, and you can get close to 90-95% coverage. We're able to then report all the missing and blind spots that we weren't able to cover and annotate that based on the CAD. So the CAD, it does form a baseline for us. Once we're able to get the first scan through, we don't need the CAD anymore. We can use the point cloud as the baseline going forward for future scans. We have, though, faced criticism because from FPSOs, because FPSOs are a much larger asset, much more densely packed. It takes a lot longer. I'm not sure exactly how long it would take, but a bit longer than these topsides with the same team. I think it was about 200 man days per FPSO. So what we did was we developed a much more faster mobile scanning sensor, which we call the rapid data capture technique, where a person can just basically just hold a TLS type sensor in their hand and just walk through the whole asset, which wouldn't require more than 30 man days. So with 2-3 people, you could just do this very quickly in just a matter of 2 weeks on an FPSO. Don't hold me to it. My guys know the latest statistics on exactly how long it would take. So that is the new market we're looking to break into now with this newly developed sensor. We don't intend to scale the sensor. We do intend to kind of offload that to contractors so that they could collect the data. But that would be quite disruptive in the FPSO market. That is quite interesting. We did a recent scope study with one of the operators. They basically looked at a scope, which I won't go into much detail, but basically they estimated about 13 people for about 6 months, which we were able to collect data for on the platform that they would then be inspecting. That's quite a bit of time. The same scope we were able to collect the data for in about 2 to 3 weeks with just 4 people, 3 to 4 people, 4 if they include their own inspector on board. So that's a significant improvement. Where do we see this going? Well, the main driver for this technology really is reducing LOPC, or loss of primary containment risks, unplanned shutdowns through early detection. Early detection using TLS is, you won't do it more than once every 2 years. Right? So we do need a system that is on board, preferably, And Total was one of the first clients that mentioned this. They said, we would actually like to have re-inspections done every quarter. So what we see is the only way to be able to do that, given the amount of fighting that operators have to do to get inspectors on board, scheduling is one of the biggest hurdles and logistical challenges. There is no option but to have robots on board doing these. And what more recently has happened is that some of our clients actually are now starting to use drones to follow up on blind spots and add that data back into the thing. This is actually happening as we speak. So we are moving in that direction. I hope that kind of roughly answers your question.
Okay, I guess this is my cue now, right? My turn.
Yeah.
So, Nasir, I have lots of questions I could ask you. I have lived the same experience Abyss has been living, starting with Deep Lab v3 plus convolutional network to detect corrosion, to understanding that just detecting corrosion on image is not enough. You gotta need to build a scalable system. And then comes the question about how do we get 3D information. That's an amazing story. I really enjoy this. But I want to ask you about the future. I've seen great results with multimodal models today that can turn an image into very clear and interesting explanations of the scene. They're great at scene understanding and transforming images into language. And that opens up a whole bunch of opportunities when you think about large language models that are available today. You can add up to your very highly complex tasks and use them to solve problems. Are you currently looking at this field? Are you seeing this technology of multimodal models as an opportunity for you, adding language to your current developments?
So I do think that is going to play a role, but not probably in the shorter term on our product roadmap, probably on the longer term, because as the defect library is growing, currently we're just focusing on corrosion. For corrosion, we're able to achieve the required outputs for these operators. However, as we start to grow, as I mentioned, there are dissimilar materials, there's daylighting, there's a whole bunch of things. We do need kind of multimodal modeling so that we can be able to start to look at these new defects to get more context. As I mentioned, without context, there's no way that we are able to further improve our precision. So I think multimodal will play a critical role, probably in about 12 to 14 months time as we start to expand into new defects. And it will also allow our technology to be more scalable across a wider variety of assets than just offshore platforms. I do see that playing.
Okay. If you think about it, getting context from CAD models and point clouds, it can be quite expensive, though it has a high value added for the consumer because it can do deep analysis and measure with accuracy, measure distance and surface area with accuracy. But a lot of stuff can be done with images only. How reliant are you today on point clouds and CAD models to actually apply corrosion detection?
So we are basically making two offerings right now. One is for the mechanical integrity side, one is for the coding side. For coatings, we don't require contextualization at all. We basically just require data off the platform. We can do this with visual imagery. We don't even need the TLS for that. However, TLS does add a lot of precision, but the sampling plan is much less denser. Therefore, the cost of the survey itself is much less. However, for mechanical integrity, since we do require context, it is important to be able to contextualize the asset. It is important for us to do that. So we are relying on the TLS right now. However, what we're trying to do is, if this can be a one-off CapEx, we're trying to figure out how we can use 2D imagery to further improve upon the baseline that we build off the TLS, so you don't have to use the TLS at every rescan. The architecture first started off with our software architecture was entirely dependent upon an entire platform being contextualized. What it wasn't designed to do was to start taking data as it comes in. So it wasn't really designed to be a database, more so a one-off deployment. We're starting to make improvements in our architecture where we can start to flow in information. So if an operator decides to use handheld cameras to go out and just follow up on some inspections, they should be able to put that in. There's a sampling protocol for them so that monocular imagery can be meshed and stitched into the fabric. This is also an active project we're currently working on with one of our clients.
Oh,
So our goal is to kind of, well, the best way to say it, but it wouldn't be very accurate, is to not have the TLS in the future. But to build the baseline, to have something started, you do need a TLS. If you want to get a full, complete picture of your model from an asset integrity perspective, reducing its requirement in rescans, follow-up inspections, having 2D imagery, handheld cameras, drone imagery, and even other sensing modalities, like some of our clients are actually interested in getting thermal imagery in. So kind of building in that flexibility on the sensing modality side is one of our core shorter-term architectural goals.
There is lots of priors that you get from laser scanning. So what's the point of doing it again if you can use those priors to,
Exactly.
yeah,
Exactly.
to leverage and reduce the cost of updating the software?
Exactly.
Well, that's awesome. Yeah. Henrik, do you have any other question?
Of course, I have a long list. So, let's.
I shouldn't have asked him.
Let's jump into the next one. So, have you done any work on projecting? Because I saw you had like you did the interpolation between two test points, right? But have you done any kind of work looking at projecting how corrosion could potentially be developing over the next, let's say, next time frame? I'm guessing this could be very interesting, especially when you, even if you have multiple test points, you would want to know like what would happen to this until my next inspection point if it is at the street. Yeah.
That's a very good question. In order for us to, so currently we're not doing any projections in the future, so we're not doing any predictive analytics. And but the point, the stage that we're in right now is that we accumulated, for some platforms we've got 3 scans over time, over the past 5 years, let's say. So we are looking at how we could use that to extrapolate what the next state would be. But that really is also an area where we're waiting for the clients to define how that, how do they want to look at it? How do they want to quantify change and how they want that to be projected? So it is something that we can do right now. It is on our roadmap. We're actually working actively with one of our clients. But I think, that is the next step. We're not doing it at the moment. Or providing it as an active service at the moment, but it is something that is in the R&D phase. I think that is the what our clients did say right at the start was that is the holy grail. If you're able to extrapolate, so for example, if you can measure the rate of change of the surface area for coating breakdown over 2 scans, you should be able to extrapolate that to an X period of time in the future or project that in the future. The problem, though, is if we're just relying on TLS, right? Our inspection cycle is every 18 months to 2 years, right? That's not early detection, right? You'd need a higher frequency for that. In order for that to happen, you definitely need something on board. And having something on board means you're not going to be able to use a TLS. You're going to need to use drones. You're going to need to use handheld. So and I would say, identifying spots which we think should be monitored more quickly as opposed to more slowly is going to be the goal of this. And what is the frequency with which they should be monitored? But that's going to be on the platform. TLS, I don't see that playing a role in that. It's just too heavy to do it. I hope that answers your question.
It does. Thank you. So just one more, then I'll cut it off. So you mentioned that there was a wide range of criterias, and with a really large gap between or lack of agreement between many different operators and different clients. So how could you maybe explain a little bit, how do you manage all of these different criterias within your solution? Because I would assume that a lot of your models and let's say trained models are not necessarily trained on different criteria. So how do you manage that? Like, could you elaborate a little bit on that?
Sure, definitely. So like I mentioned, one of the major jumping points from Gen 1 to Gen 2 was actually to overcome that scalability bottleneck. So what we do is we would just basically look at different types of features that compose corrosion. And that's what we look at perfecting in terms of detection. Once we detect those features, really it becomes a simple problem of how, okay, this is what do you want? So the clients basically say, class A, this is what it looks like. So the clients write us an SOP. That SOP contains basic images. So it's got a set of images that describe the problem. It's got a basic wording description of what the features look like. And then basically what we do is we just take the output or whatever we predict and classify them with a label. That is a separate process that sits on top. It's a very straightforward process. We just have to feed that new SOP into the mapper that takes the output of our models and maps the labels for each of the outputs into different classes. So it doesn't require model intervention. We don't need to touch the model for it. As long as we're detecting features that are, composing different types of corrosion, you can always take the output of the model and group them into different classes. So really it's the SOP. And that doesn't need to be, that currently we don't have a front end or an API where the client can just come in and say, "Ooh, this is what I want. Here's the SOP," and then it happens automatically. Currently, that's still an internal process where we take that output and we get our engineers in the back end, whether in Sydney or in Islamabad, to actually do the translation. But they don't have to do it manually. It is programmed, but it is not an API.
Thank you, Nasir.
No worries.
Robinson, do you have some further questions?
No, I think I actually I would have thousands of questions, but I think we explored a lot. I just have a history with this theme, this subject, and I find it very interesting. I hope you guys get to the holy grail that you're looking for. It would be very interesting to see someone crack that case. It would be awesome for seeing prediction and how you can predict a surface, change in surface area over time. Yeah. So now, Eric, you can do the honors.
Oh yes, so I just want to thank Nasir thank you, Nasir, for the excellent presentation. Very interesting. I had high expectations coming into this, and you didn't disappoint. So that's a note of confidence. I look forward to having an opportunity to chat with you sometime in the future as well, where we can maybe look into more of the questions that I didn't ask today. And thank you very much again. And I hope everyone who was following the webcast from the audience was also as interested as I was.
Thank you very much. It was a pleasure and an honor being here. Thank you for inviting me and allowing us to share our learnings with the world.
So, okay, that's it. Thank you, Nasir, for accepting the invite to this webinar. So for the audience who watch us, please follow us, the social media, Technical Committee's office, and our email too, if you want to contact us to participate in your technical meets. We disponibilize the form in the YouTube chat. So that's it. Good night, good evening, good morning, everyone, however time you watch this. So that's it. I will end the live now. Thank you very much once again. Bye-bye.
See you guys.
Thank you. Bye.